Hi all, and thank you for joining me today for this presentation. So I'm going to talk to you about AI for cybersecurity. I am Hani Ragab, and I'm an associate professor with the Heriot-Watt University. I'm also the director of the Institute of Applied Information Security at Heriot-Watt. I got my PhD in 2007 and have more than 17 years now in the field of cybersecurity. Right now, I like to call myself a cybersecurity data scientist since I try to combine both fields. So why do we need AI for cybersecurity? Let's start with a couple of examples. So the first one is this finding in the incident response analyst report by Kaspersky, which says that roughly 1/4 of the attacks that were reported in their study used malicious email. Another fact is that almost 500,000 new malware appear on daily basis. It's malware and unwanted applications. Unwanted applications are roughly 1/5 of the number. So it's 400,000 malware a day. Okay, the question now is how much of those does your anti-malware know? Your antivirus product, how many of these 400,000 new ones does it know? The answer is depends on how frequently you get the updates. So if it is daily updates, obviously you will not know about the 400,000 files that were generated since your last update. Yeah, so you can go up to 4,000 unknown malware. If you are doing on hourly basis, then you are going to get 18,000 unknown malware. The slightly good news here is that most of the new malware are actually variations of existing malware, and some statistics put the number of variations on existing malware at 90% plus. Yeah, but still there will be many of them that are completely unknown to your antivirus product. Yeah, and even to the producers of your antivirus product, because they might not have had a sample of that malware yet. So it might be circulating, but no one knows that it's circulating. So what does AI do here? AI is going to replace, or not help those very costly skilled security analysts that were supposed to go and detect, say this is a new malware, this is a new thing, this is what here's what this one does, etc. Help them make their job easier, or handle the slightly less complicated cases automatically, yeah, to reduce the cost of the detection of new pieces of malware. So that's one thing that they can do. But also the AI models, what they can do as well is, since they are much more flexible than rigid rules that your antivirus might use. The classic antivirus, they know files by signatures, and these signatures are quite rigid. It can be sequences of code that might just be changed slightly by the malware creator. It might be the hash, and changing the hash is extremely easy. Just add a knob in the code, no operation, doesn't do anything, but changes completely the hash. So the AI approaches, and before them some slightly smarter signatures obviously, but the AI approaches have this very high flexibility, and they can generalize well. So they learn from a sample of malware and then learn from this some common characteristics of malware that they might be able to find in completely new and unknown malware, or a category of malware, which is less likely to happen by the classic anti-malware products. Same thing for the malicious email. So this malicious email, instead of creating rigid rules that say if the email comes from this address, or if the email subject or the email body contains these particular strings, then this is a malicious one, or this is a spam. The AI model can do much more interesting stuff, either by using simple techniques, techniques like decision trees, or even more sophisticated natural language processing techniques. So our outline today includes 3 steps. We're going to talk first about the process of applying AI for machine learning, the different applications of AI in machine learning, and then briefly the limitations, the challenges, and the bright side, hopefully, the opportunities that AI offers in the field in cybersecurity. So first thing, the process. And I think it's interesting just to use this standard model. So it's the cross-industry standard process for data mining, or CRISP-DM. I'm not going to explain this process in general. I'm just going to talk about it in the context of cybersecurity scenario, and I'm going to use the scenario of malware detection since it's my favorite thing. So in the business understanding, you need to know what you want to do, right? There are other things, but in our case, what we want to do. So we want to do, for example, malware detection. That's one scenario. Another scenario is, for example, malware classification. And classification means that you take a malware or you take an executable, you don't know yet if it's malware or not, and you want to know what type of malware it is. Is this so we know, we reach the decision that this is the malware. Now, which type of malware is it? Is it a worm, virus, crypto miner, etc.? Yeah, so you need to know which category it is. Then the data understanding. So your data is probably, if you're going to detect malware, and say we're going to detect malware in Windows executables, then your data is going to be exe files, maybe DLLs. There are like 12 formats that are executables under Windows, by the way, SCR, other things. So we want to understand our data, what type of data we're going to use. Also, for example, some malware used packing and obfuscation techniques to hide their activities. So it's like the executable itself is compressed, is encrypted to hide what it does. So it uncompresses or decrypts itself on the fly when it wants to run. So are we going to handle this case, or do we just want to use non-compressed, non-packed malware and executables? Then the data preparation, which is quite challenging. We're going to talk about it a bit later. But in the data preparation, you're going to decide how you're going to represent your executables, for example, because an executable is a binary. You cannot just give a neural network an executable and say do something with it, do some magic. It doesn't work that way. Yeah. So the executable has to be pre-processed, yeah, to provide some meaningful features that the machine learning algorithm can work on. Then modeling, this is when the magic happens. This is when you apply your machine learning model. It couldn't be a classic shallow learning algorithm like decision trees or something like that, or it can be some deep learning algorithm. Then comes the evaluation. You test your data set, you test your results, you test your model and check if it performs well, it's generalizable, you can use it somewhere else, and so on. If you're happy, you can maybe go for the deployment. If you are not, then you might review any of the previous steps. So let's talk a bit more in details about the malware detection scenario, provided as an example of the process. So first thing, we need to decide what type of malware we're working on. Is it Windows, Linux, etc.? And of course, under Windows, there will be executables, and there will be also malware that run in JavaScript or in Word or Office products as inside the scripting languages. Yeah, I tend to think about executables when thinking Windows, but of course there are other types of malware, as I just said. So the data set, you need to build a data set probably of both categories, malware and benign. So for the malware, you can use malware from online sources available for researchers like VirusShare, Malshare, Malware Bazaar. There is a long Malware DB and so on. There is a long list of things that can be used. Then the benign files, you can get it from GitHub, from app stores, SourceForge, OS files, etc. For the first three, there is one thing to be careful about, which is malicious files might be there. Slightly less likely in the app stores, but not impossible, obviously, as you know, probably, like Android App Store, you can find malware there. But it is much easier in SourceForge and GitHub. You can just create a GitHub account and post the source code of a malicious file there. Now people cannot just go download that, compile it, and assume it's on GitHub, then it is good, right? So these are not necessarily benign. OS files should be, by definition or by trust of the OS maker, benign files. Yeah, but even here, it is not that straightforward. Yeah, you might have heard about Pennsylvania University being banned for life from contributing to the Linux kernel because some researchers from there introduced intentionally some vulnerabilities in the patches that they proposed. It was a big story. So yeah, you need to be careful still there. The labeling, so you can do labeling of your data set. So you can confirm that your benign files are actually benign by scanning them with anti-malware. Or you can also further classify your malware. You know that they are malware, but for example, VirusShare does not tell you what type of malware they are. Yeah, VirusShare, by the way, has an impressive collection of something like 14 to 16 terabytes of malware, and I know it because I have the pleasure of having a backup copy of that. So the labeling, when you do it, as I said, it's using some anti-malware product. You can use some better options like virus total, which gives you a report by 60 anti-malware or so. So maybe the anti-malware you're using is not that good, not catching all malware. Yeah. I was using a Unix or Linux based anti-malware, I don't remember now what its name, to scan the collections of VirusShare, and it was, in general, it catches 40,000 out of 60,000. It misses 1/3 of the malware. That's how bad it was. Yeah, but then you use VirusTotal, it's much more reliable. Then the next question is, what kind of features? Now the features is how you are representing your executables. Yeah. So the question is, what kind of features are you going to use? Is it static or dynamic? Static features mean that, or static analysis in general refers to when you are looking at the file without executing it. So you can look at the executable file and just check what strings are in it. And you will find some interesting information there. Like for example, the URLs to which the file is connecting. If the file is not obfuscated, you will see the URL there. Yeah, so maliciouswebsite.com, you will see it. Yeah, you will also see which libraries it calls. Kernel 32.dll, and then with the libraries, and then the function names, open process or load process, load library, things like that. Yeah. So this is the static one, and it already gives you quite a good collection of features. There is a tool called strings that allows you to see all the strings in an exe file. But you can do other things, obviously. Not just the static is not just about looking at the strings. Yeah, you can do. There are tools that are sophisticated enough to go and explore the header of the executable file, the PE header, and get you the information from it. The same applies to Linux executables, the ELF header, editable linkable format header, and get you information from there. So this is the static one. Then we have the dynamic features. Dynamic is when you are running the file. So you can run the file, and by running the file, you get more information. For example, in static, you will know that your process or your executable wants to open a file, wants to open a port, wants to, I don't know, create another process, but you don't know in which order all this is running. When you do dynamic analysis, you get a sequence. You know that it created a process, then one of the two processes, the original one created a file, and the other one opened a port. Yeah, so you get a sequence instead of just knowing, oh, they are there, but I don't know in which order they're running. Or also, you will know how many each of the calls was made. Yeah, dynamic analysis is not that easy, but it gives you this kind of information, hopefully. So here there's a big decision here about which kind of features you are using, yeah, because both are used in the literature and by anti-malware products. So when you hear about sandbox, then we are talking about the dynamic ones. Yeah, sandboxing is used to run a malware inside that sandbox, and once you are done, you just wipe the sandbox and you're fresh. Yeah, so no impact on the host machine. Then there's the OS specific features, because for example in Android you will have the APK file will tell you in advance which kind of permissions it's looking for. It has a manifest file and so on. So these are things that are only specific to Android. Yeah, and other operating systems will have their own things as well. Then comes the next step, or we still actually about the, so here we're extracting the raw features, the very basic features. Then what do you want to do with those features? So there's the feature extraction, where you are going to extract the features. It's actually here where you extract those raw features. Yeah, and then you can use different representations from machine learning, like one-hot encoding, bags of words used in natural language processing, etc. Then out of these features, so say that you end up with 50,000 features, too much to use in most of machine learning algorithms, especially if deep learning. So what do you do with that? Then you want to reduce their size somehow. So you can have techniques like selection, which will take a subset. So you have 50,000, you end up with 1,000, but 1,000 that existed in those 50,000. You're just taking a subset. You can alternatively use some dimensionality reduction technique, such as principal component analysis, PCA. And in that case, you can get 1,000 features out of the 50,000, but those 1,000 features did not exist in the 50,000. It's actually each of those features is a combination. So each of the new 1,000, each of them is a combination of the 50,000, all or a subset of the 50,000. Okay. Alternatively to this pipeline of feature engineering, sometimes combined with part of it, but alternatively in high level, you can have some representation learning. So representation learning is you use, instead of telling the machine learning pipeline, instead of telling it how you want the features to be represented, you try to ask some deep learning technique. All these things use deep learning, the representation learning ones, to get a better representation or get a reasonably good representation. So one of those techniques, for example, word to vec. So this was proposed in natural language processing, and then it's a very, very interesting. If you don't know this technique already, I really strongly recommend that you read about it. But word to vec represents each word by a vector, hence the name. Okay, but then it has some very interesting characteristics that makes you feel that the machine understands the meaning of words, but it doesn't. But it's very interesting. So for example, if you take the vectors, now I'm giving you an equation, but it's representing vectors, yeah? Or you should think about these words as vectors, not exactly words. So you take the word king minus man plus woman. So if a king is not a man but a woman, what is it? Equals queen. Yeah, so this equation would work in word to vec. Yeah, which makes it very interesting. So it understands from studying the sequences that exist in text. Yeah, these techniques are capable of learning some sort of semantic of the words. Yeah, and we can apply the same thing exactly on graphs of system calls, for example. So system calls are think of it as the actions that an executable does at the lowest level. So this file, this executable does this action, then this one, then other one, etc. So you take this sequence of actions and make it like a sentence, because it's a sequence. Same way as a syntax, apply word to vec to that, and you get yourself potentially better representation of those individual system calls. Yeah, and then this representation can be used in the machine learning. So here we're just doing the representation. We're not running the classifier to detect malware or anything. No, we're just here doing a better representation of the features we have. Then the next step here is the modeling. So you can use either shallow learning techniques or deep learning ones. As I mentioned earlier, then you have evaluation, you have different metrics, accuracy, F1 score, area under the curve, and so on. And then you want to know if your results are generalizable enough or not. Yeah, so you can, for example, think about building a data set that as diverse as possible, as large as possible. Yeah, try your push on large chunk of completely unseen data to see how good it is, etc. So this was the scenario for malware detection. Very briefly, if you wanted, for example, to do an intrusion detection, by the way, I have a PhD student working on the previous scenario, and I have another PhD student working on this one. So here in intrusion detection, what you want, or network intrusion detection, what you want is to detect intrusions and classify them from a data set of network traffic. So you have network traffic, chunk of a collection of network traffic. You know that some of them, they have already been labeled for you. You know, some are malicious, some are benign. You want to learn which ones are good, which ones are bad. So you can do representation learning. For example, you don't have to, but just this is one thing we're trying, actually, we're working on. So do a representation learning using Word2Vec. So you look at the exchanging between the machines as if they were text by people. Yeah. So look at this. So each message I send you is a sentence. You reply to me with a sentence and so on. So we take that sequence and apply Word2Vec to it. Yeah, so it makes traffic to vec. So we convert the traffic into a vector, which is hopefully a better and richer representation of those. And then we can use LSTM, which is a machine learning it's a deep learning technique, long short-term memory. And LSTM learns very well sequential data. A sequence, remember the traffic. Okay, so very briefly now, because we are running out a bit, out of time a bit here. So some common applications of AI for cybersecurity include malware behavior analytics and detection. So I've been talking about that for a while. You can work on native executables. So the PE for Windows, portable executable, the ELF for Linux, APK for Android, and so on. Or you could work on other formats, like, for example, JavaScript, malicious files, Office scripts, and so on. Another one is the network intrusion detection. We just mentioned it. Then you can also look at user and entity behavior analytics. So you can look at individual users, for example, in an organization, and see if their behavior is malicious or not. Like, are they internal insider attackers? More complex and more complete scenario would be to include the AI into the SOAR, S-O-A-R, security orchestration, automation, and response. So the collection of data, automation of the processing of data, and the response where you apply the playbooks to react to attacks, escalate to humans if needed, and so on. So all this, each of these steps is a good place to apply AI or big data in general. Yeah, because you're really dealing with very large volumes of data there. Then there are some techniques, some applications that are more naturally NLP ones, but they can still use other non-NLP, NLP, natural language processing. So they are more NLP, but they can use other stuff. So spam or phishing detection, since that you are looking at emails, text. Yeah, so NLP is a natural choice there. Open source intelligence processing, so OSINT, yeah, OSINT. So this is the sources come under different forms. Some of them are structured, some are not. Again, NLP can be very good here to process them. Text summarization, for example, can summarize articles for a human expert. So instead of reading 10 articles on the same topic, you can do multi-document summarization and get the 10 documents to get summarized. I had someone actually worked on that before, and we got some interesting results. Automatic vulnerability detection, so scanning a file, scanning executables, reading the code, source code of an executable, again, text, reading it to try to see if there's a vulnerability on that or not. PhD starting soon on this. Malware author characterization, so author characterization of text is a very known application in NLP, has existed for ages now. Malware author characterization is just about using those techniques, adapt them a bit to detect the authors of executables or code from either detect the authors, okay? And this is very useful in security, because the next time a virus hits you or a malware hits your organization or your country, you can try to trace that back to some entity in particular, right? By analyzing those entities' other malware. Yeah. So another PhD starting on this one, by the way, as well. And you can also other applications, digital forensics and incident response. I need to finish very shortly now. So the limitations and challenges. One big challenge here is the data variety. So you have all sorts of data here that you're going to work on in the case of cybersecurity. You have data that are collected as logs from your Windows, logs from someone with Linux, logs from phones, logs from firewalls, logs from Cisco routers, or logs from all sorts of things. Yeah. Add to that the executables and things like this. It's binary files. Yeah, a PDF that was found to be malicious, another type of binary files, and so on. Yeah. So these the executables and similar files, they bring up a very interesting question. What is the best representation of an executable? How do you represent an executable? Yeah. You can use what I was describing earlier in the representation learning technique, where you look at the sequences of calls. You can represent it as a graph, a sequence, a whole sequence, and just leave it as is. You can represent it by sort of one-hot encoding, when you see if this executable calls this function, put a 1. If it doesn't, put a 0. So you get an executable represented as a vector, but this vector doesn't know how many times the call was made, how many times you did this action, and it doesn't know in what order you did those actions. Yeah, so there are lots of representations, and it's very difficult to know if one of them is lossless. So you have every piece of information that you could have had from that executable. Yeah, actually I have a BSc student a bachelor student who did a very, very good work on extracting all static features from the Windows executable headers, because that's not easy, and there's not a tool that does that to produce a JSON file, for example, from the executable header. Network traffic. How do you represent network traffic? As NetFlow or PCAP? My PhD student prefers this one. I love PCAP because I feel this is lossless. You have all the information about the traffic and the packet capture. Okay, whereas NetFlow is a summary of what happened, of the whole conversation, not individual packets, and it loses lots of information. And we have a debate about whether this is enough to really detect and classify attacks. I'm still not convinced. Then there is another issue, which is the model decay. So you created your model today based on all malware, keep it in the malware scenario, and all malware known up to end of September 2021. In October it will do well, November still fine, December a new malware came and this thing doesn't know anything about it, your model doesn't know it, so it doesn't detect it. January, a new approach of malware came out, and there are like thousands of malware under that category. Your model doesn't know anything about it and cannot detect it. Yeah, of course we're using AI because we want it is flexible and it can detect unseen things, but there is a limit to that. Yeah, it's not a magical solution. So the model decay is a problem. You cannot just train a model, put it there, and it will detect everything forever. Yeah. Obviously, high false positive rates depends on which model you are using. How did you do your training? You might get a high false positive rates, which can be very annoying. The other way, the opposite of that, the high false negative rates is also a big issue security wise, because it means that you are missing malware, for example. Yeah. And explainable AI. The more modern AI models used in cybersecurity tend to be more of deep learning models, and those deep learning models all share the same issue. They are not really explainable. So we have a black box that tells you with very high accuracy, it's perfect, that this is a phishing email or not. Yeah, but how did this black box make the decision? You have no idea, and it's very difficult to understand anything. Yeah, so building explainable models is quite a challenge. A couple of there's another thing as well, which is the appearance to modeling. So the delay between these two things. How long does it take for a piece of malware to appear until the time a model has been trained on it? Yeah, so the malware has to appear first, and then someone to sample it, find it, detect that it's a malware, and so on, and then put it to the model to train. This is not really a problem of the AI model itself, but it is in the whole pipeline from creation of malware to being able to detect it with an AI model. It can take some long time. Opportunities, things that so there's a good sign that the AI, the antivirus companies, anti-malware companies like these guys. I'm not making any free ads here. I actually don't use any of them, so this cancels any ad doubts in your minds. So these guys, they say that they use AI, and actually Kaspersky is saying that they used AI to detect 1/3 of Android malware that they managed to detect, which is quite good. I couldn't find the details of that, but maybe I had to dig that a bit deeper. And then the other thing is online learning. Online learning is, or stream learning. So it's a technique that can be used to continuously update your machine learning models. Yeah, and here obviously we need that in cybersecurity. Most of the papers, so we did an exhaustive survey on Android malware that we submitted for publication. Out of, I don't know, 40, 50, I don't remember now the number, it's a very large number of papers, only 3 or something like that considered the online learning aspect or did something on it. Yeah. Whereas it's very important. You cannot just deploy a malware detection engine out there and leave it for a year, right? So online learning is a really interesting thing that can be used to continuously update your model. You can have, if you have the time, you can have a look at our website here, astan.org, where we put there one of our first models for Android malware detection. Yeah, so you can have a look at it. So I hope you enjoyed this and found it useful. AI for cybersecurity has a huge potential. There are lots of things that can be done. Many things have been done already, but there's still much more to come. Looking into better representations of the files, the those executables, the even scripts, better ways of representing them. There are so many applications that can be done here, and lots of work to be done. I hope that you like this presentation, and who knows, maybe you find yourself one day working on one of these interesting problems. All the best and see you soon.